All right, let's get started on chapter 4. Chapter 4, we're learning about using this stuff for graphing. Chapter 4. At least the first part. Let's see, is that what we're doing throughout all of it? Feels that way. Yeah, it's like how does calculus help with graphing? So 4.1 is on increasing and decreasing functions and stuff like that. So let's say we have some function, it's doing some stuff like this. Ten. Doing some stuff like this. MF. Yeah. You get me. It's now beeping at everybody. I never know, so you turn it on right away. The hell is everybody? 6, 7, 8, 9, like 2, 4, 6, 8, 12 people. 7 online, 19 people. Good. Alright, so on this region right here, it's decreasing. And it looks like it's decreasing here as well. Decreasing as in going down in value. And we do that by looking at the Y value. And regions where it's increasing. It's going up from there to there. And it looks like it's going up there. So increasing is going up in value. So I could say f of x is, this is decreasing on negative infinity up until 2. And it's decreasing from 4 to 7. You know what, let's change the graph after this. Let's make it where it's not increasing or decreasing, let's make a flat line. So that'll happen at 10. So here it's increasing from 2 to 4. And it's also increasing from 7 to 10. Where it's neither increasing or decreasing. We say that the function is remaining constant. It's staying at a steady value. And that is happening here from 10 to infinity. So let's take a couple of these regions and I'm gonna blow them up larger. Give us some room to write. And like, take a look at what's happening. A little bit closer. So like from 2 to 4. It's doing something like this. 2 to 4. And what I want to think about is what's going on with the derivative. This, we're looking at how calculus affects it. So what's going on with the derivative? So I'll just look at different points along this. What could you say about the derivative in each of these cases? It's positive, it's going up, right? F prime of x is positive. And if we wanted to use some math jargon with it, we would say greater than 0. So f prime of x is greater than 0 on increasing regions. And like from 4 to 7, where it's going downward. If we look at the tangent lines here. We would say that since it's going downward here, it's negative. So f prime of x is less than 0 on decreasing regions. And on constant regions. 7 to infinity. We look at the tangent line. The slope here is 0. Which is f prime of x.
John, shouldn't that be 10?
What? Oh yeah, it should be 10. So this actually gives us a test for increasing and decreasing regions. So we have a test for increasing, decreasing, and constant regions. If f prime of x is greater than 0 on a region A to B, then f of x is increasing on A to B. And likewise, if it's less than 0 on AB, then f of x is decreasing on AB. And then if f prime of x equals 0 on a region AB, then f is constant on AB. And I want to very much emphasize, especially with C, this is a region, not just a single point. In 4.2, we're going to look at single points where the derivative equals 0, but nothing around that it has a derivative of 0. It actually does special stuff for our graph. We'll be doing 4.2 today, at least part of it, so you'll see the connection a little bit. So how can we use this? So let's find intervals of decrease and increase, or increase and decrease. F of x equals x squared plus. Oh, it's not plus 3x, and we'll do minus. What do I want to do? Okay. So what we'll do is we'll take the derivative. What is the derivative? 2x plus 3. And what we're gonna do is, okay, we wanna find regions where it's positive or negative, we need to do a sign chart. So let's make a sign chart. It looks like this is gonna equal 0. If we're trying to find where it goes, changes from increasing to decreasing and back, checking where the derivative equals 0 is gonna give us like boundary points. So we're gonna set equal to 0, and we can see that at x equals -3/2, something is going on. -3/2 would be right here. So if I check points next to it, like if I plug in f prime of -10. I'm gonna get -20 plus 3 is -17. The slope is negative over here. And if I plug in, ooh, 0 is an easy one to plug in. F prime of 0, 2 times 0 plus 3 equals 3, which is positive. It's gonna be positive over here. So f prime of x is less than 0 on negative infinity up to negative 3/2. And f prime of x is greater than 0 on negative 3/2 up to positive infinity. Now, I'm gonna work with this a little bit and do some completing of the square here. I'm gonna try to write this in the form. Right as. F of x equals x plus h squared plus k. No, x minus h squared, that's how we say it. X minus h squared plus k. And that's gonna take completing the square. This is probably something you haven't done in a while. So what I'm gonna do is I'm gonna make a little space between the 3x and the -10. And this is called completing the square. And in fact, if you only took algebra in high school, your algebra teacher may never have taught you it. You take this value and you divide it by 2. And you square it. That is 9/4. Or negative or positive 2.25. So what I'm gonna do is I'm going to add in 2.25. To put with that. And to make sure I don't change the value, I'm gonna subtract 2.25. So that the net change to the equation is 0. So plus 2.25 minus 2.25. Overall change 0. If you've done completing the square before, this part will look familiar, hopefully. We're gonna take this value that we squared and drop that right here. And write it as a square, and then whatever we have left over on the outside. That. And so this matches up with. X minus h squared plus k. Where hk is the vertex of the parabola. So this says negative h, but that's positive. So h is actually gonna be negative 3/2. Or negative 1.5. And k is gonna be negative 12.25. Right there. It's -2, this is y, x. And if I wanted to find where it crosses the x axis. I could set f of x equal to 0 to find the. X intercepts. And I'm gonna factor that. That is x plus 5 and x minus 2. So we can see x equals -5 or x equals 2 are x-intercepts. So -5 is over here. And +2 is there. This is a parabola that is doing this. Does this match up with the calculus we did?
Get a -1/2. As a vertex.
-1 1/2 or. Like right there, -1.5.
Because it's supposed to be a negative h.
Yes,
Okay,
so that's writing, another way of writing that, this. Is like x minus -3/2.
okay,
And we're trying to make it look like -h.
okay.
So we said -infinity to -3/2. The derivative was less than 0. Or the slope was decreasing. Is that true? We're going downward all the way up to -3/2. That matches up, f prime of x is less than 0 here. And we said where f prime of x was greater than 0 was after that. And it does look like it's going up for the rest of it. So this matches up with what our calculus showed us. Now, presumably you already knew how to graph a parabola from algebra or pre-calculus. But. There's a lot of functions that are hard to graph as they are. And when you've learned or taken algebra or pre-calculus. We were kind of hand waving with a lot of stuff. We found the x-intercepts, we found the y-intercepts. And we were able to show like what happened at the end, but we never showed like where things turned around. So we're gonna look at that here. Using this same graph though, I want to talk about the second derivative. So I'm gonna have that graph there off to the side. Let's talk about the second derivative. F double prime of x. So f prime of x is a change in y or a change in f of x over x, a change in x. The second derivative is a change in f prime of x over a change in x. So this ends up resulting in like two scenarios. If we have something like this. As we're going along the line. And I'll put in some values in a second. And the red values will be f prime of x. This looks like that might be equal to 1 there, maybe 1/2 here. This is 0. That looks like -1, maybe -1/2 there. -2, -3. 2 and 3. So that the red values are like what the derivative, I'm guessing what the value is, I just like, I don't have an equation, so. I'm looking at what the slope kind of looks like. What's going on with the second derivative here? How is f prime of x changing as we go from left to right? -3 goes to -2, goes to -1, goes to -1/2. 0, 1/2, 1, 2, 3. If I wrote that on a number line. And put my points there. It looks like as we're going from left to right. It's increasing the whole way. So here. F double prime of x is greater than 0. If this were a bull sitting on a table, which way would you say the bull is facing? Like if you had a little table and you had a bull sitting on it. Which way is like the open part of the bowl facing? Up. Open part is facing up. We call this concave up. Concave. Is part of concavity. Which measures curvature. So is it curving up or curving down? Yeah, and this one is curving up. This is in general for both things. We're gonna do the other angle going downward in a second. If I have the bull going downwards, this looks like a bull facing down. Or better yet, a shot glass after you took the shot, left it slanted upside down. We're gonna call this concave down. And guess what happens here? It's gonna be decreasing. As we'll see in a second.
It's not called convex, then what's upside down?
That's another word for it. If we stick to using concave both ways, then using up or down kind of gives it away. Like, let's be honest, in the future, you're not gonna remember, if you've learned the word convex and concave. They both have con in it, you're gonna not remember which one's which, but if you say concave up or concave down, it's kind of good the whole way. This would be like having a positive slope here, but. There's a 0 and now it's going downward. It's decreasing from left to right. So looking at our graph here. Of f of x equals. X squared plus 3x minus 10 before we changed it. What type of concavity would you say this has?
Concave up.
It looks like concave up, right? From the graph. Well, let's check it. We had f prime of x was 2x plus 3. We did that part earlier. If we take the second derivative. Or take the derivative of this line. To get the second derivative. What's my derivative there? 2. Which is greater than 0 everywhere. So that matches up with what we said with concavity. So to put that all together next to each other and like stuff that you can, when you're skimming through your notes, you wanna find it. If f prime of x is increasing. F double prime of x is greater than 0. And we have concave up. If f prime of x is decreasing or going down. Then the second derivative is less than 0. And this is concave down. Of course, this all requires. F of x to be twice differentiable. You have to be able to take the derivative twice and actually have it mean something at those points.
Like a double prime of something that's like 3x plus 10. Like if we didn't have the x squared and it was just 3x minus 10, we can't have a double prime of that.
Well, the second derivative would be 0
It would be
everywhere.
0.
That's a good question. Let's look at your question. So you said like f of x is 3x plus 10?
Yeah, if we didn't, yeah, or minus 10, like we just didn't have that
3x
square
minus
root in
10?
that one.
Okay, so what does that look like?
Still positive.
That's a line. With a slope of 3 the whole way. So this would be f of x. F prime of x is giving us our slope, which is 3. F double prime of x equals 0. It's saying there's no curvature. Or no concavity. And we can see that, it's a straight line, there's no curve. That's a great question, and we are gonna do an example that has a higher polynomial. But like, what about low poly, I guess with straight line, what is it showing up a straight line? There's no curvature here. So let's do an example, it's got a bigger one. F of x equals. Oh, I don't know, let's go with 2x to the 5th. Minus x cubed plus 1. No, let's go with plus x. So let's find. The intervals of increasing, decreasing. And concave up versus concave down. So what is the first derivative here?
10x to the 4th minus 3x squared. And plus 1.
Plus 1. And what's the second derivative?
That's 40x to the 3rd. minus 6x to, well, minus 6x
Minus 6x. What about the 1?
at 0.
Here. Alright, so we got our two derivatives. We use the first one for regions of increase or decrease. Jesus, I made this a little bit ugly. You know what? Let's get rid of that plus x. This is a lot, I made up this problem as I was doing it right here, there's a reason why I didn't have a plus x before. We don't wanna spend forever factoring it, finding where the zeros are, but this one's kinda easy. Now we can factor out a x squared. I get 10x squared minus 3. And we're like we did before, we're gonna find where this equals 0 and then do points around it. So this says x squared equals 0, and we take the square root, we get x equals 0. This one, 10x squared minus 3 equals 0. X squared equals 3 over 10, so x is plus or minus the square root of 3 over 10. I have no idea what that value is. But the rest do it on a number line, I guess I need to find an approximation. Point 3 is 0.5, about 0.55. Approximately plus or minus 0.55. I should probably do more decimal places, but we'll go according to that. Negative root 3 over 10. And I know we should rationalize that, but I didn't. Wanna get through the stuff that matters in this lecture. So let's test. Negative 0.1. Positive 0.1. And then like 10 and negative 10. These will be our test points here. Cause this is kind of like divided up into 4 regions. And we're plugging them into f prime of x. If I plug in negative 10. 10 times negative 10 to the 4th power.
We're plugging into the first derivative, right?
Yeah, did I say second?
No, you said.
Yeah.
I just heard after that.
Oh, yeah, we're plugging into the first derivative. Minus 3 times negative 10 squared. Fuck. That's positive. And 0.1.
$9,700.
Yeah, I got 99,700 here. Here I got a negative value. I got negative 0.029. So this is negative. And that's gonna have the same value. Since they're squared, the plus or minus is gonna go away. And that should be plus also.
You're plugging in the numbers above the number line, right? The -10.
Yeah, plugging in these
Those,
numbers.
okay.
I'm plugging these values into that.
Okay.
So it's decreasing from here to here and it's decreasing from here to here. Here, I'll change colors, make it stand out a little bit better. But not at zero. At zero, it's flat. And it's increasing from there to there and there to there. We'll do the same thing here, we're gonna factor out. Looks like I can factor out a 2x, make it a little bit easier. This is 20x² minus 3. I did not make these friendly values. This is what happens when you wing a problem. We'll do another example where they're better values. So if I set this equal to 0. X equals 2x equals 0, so x equals 0. Or 20x² minus 3 equals 0. So plus or minus square root of 3 over 20. God knows what that is. About 0.4. Negative 0.40 and 0.4. Do the same values we did before. Negative 10, negative 0.1. Positive 0.1 and 10. And we're plugging these values into the second derivative now. And we really don't need the value, we just need the sign. So. This is negative 40,000 plus 60, this is a negative area. And I can't do that, and this is gonna be, I don't know, let's wait a second. 0.1.
Okay, so for this one, when we're plugging our values in, are we going with the original double prime or the one that has the 2x factor?
You could do it into either one and should get you the same answer. Actually, it's probably a little easier in the second one. Because whatever you stick in for the x² is gonna make it positive automatically. So as long as this 20 times this is greater than 3, this will be positive. It might be easier to do it in that one. Let's do it in that one. 20 times negative 0.1 squared. Minus 3 is negative. And then 2x is negative. This should be a positive region. And this is a negative region. And that's definitely a positive region. So the concavity is changing a lot. Here it's concave down. And there it's down. Here it's up, and here it's up. Let's look at the different combinations of these kinds of like concave up and interval increasing, decreasing. And then we'll do another problem where the numbers are a little bit easier to use. So we have 4 possible combinations of how this can turn out. I can have f prime is positive. And F double prime is negative. I could do them both positive. And now we need to look at the two scenarios where F prime is negative. Let's do both of them negative here. And let's do F prime negative here, but F double prime is positive. And I'll sketch a little like sample graph of what each of those will look like. So this says F is increasing. So it's going up on everything, but it's concave down. For that to happen, we have it going up, but it's going up less and less as we go. That meets the criteria of both. And on this one, still F is increasing. So we're going up from left to right, but this says concave up. Which means we're curving up, we're getting steeper and steeper as we go. On this one, on both of these. F is decreasing for this, so we're going down from left to right. And this will be concave down. So if F is decreasing and it's concave down. It's gotta be doing some stuff like that. And here it's concave up. Which means even though the value is going down. The bowl has gotta be upwards, it's kind of like that. So it's decreasing, but. The slope is slowly increasing.
So you're getting what F is either increasing or decreasing off of the first one,
Yeah,
and then if it's concave up or down based off the second one.
yeah, it gives us our curvature. Which way it's curving, up or down? That make sense?
Yeah. I get what you mean, I think I'm just trying to like visualize it and see it like separately. Since there's 4 different versions of it,
Yeah,
but I understand that the first one it's increasing or decreasing, the second one it's up or down.
yeah, on both of them, the first derivative is increasing, so the slope is positive. So it's gotta be going up from left to right. But there's 2 ways it can do it. It can be slowly curving down or it can be slowly curving up. And the second derivative tells us which one is which there. On the lower 2 graphs, the derivative is negative, first derivative is negative. So the slope is negative, it's going down from left to right. But there's 2 ways that can happen. It can be going down even faster. Or it can be still flattening out. Kind of thing. Let's see. Let's take a look at. F of X equals. X cubed plus X minus X. Minus X. So if I take the first derivative here, what do I get?
3x squared minus one.
And if I take the second derivative here, what do I get?
Yes, sir.
So if I set this equal to 0, I can solve this. I get x squared equals 1/3, I take the square root, x equals. Plus or minus square root of 1/3. Which is √3/3. Which is a trig value that shows up all the time. Which is about 0.6. So if I were to pick 3 test points. I would probably pick 0 because that's a good point to pick. -1 is an easy one to pick. And +1 is an easy one to pick. And plugging in 0, like using those values right here makes this really easy. F prime of x equals 2 here. It equals 2 here. And it equals -1 here. I'm just plugging them in quickly. So it's positive, negative, positive. Which means if I do some arrows, this kind of helps. Helps you see a little bit better what's going on. And this one's easy. X equals 0 is where it changes. And you stick in negative values, you get negative, you stick in positive values, you get positive. So it's curving down here and curving up here. Can we see that curving down and up over here on our arrows?
So we.
Yeah.
Oh,
So if you're doing arrows to kind of show where the slope is. Now granted, somewhere these gotta intersect, so at some point. This is doing something like that. Maybe not exactly like that. This is where the 0 is. And it's called an inflection point. Inflection point is where concavity changes. Let's take a 10-minute break. I realize that we've been pushing some time here. All right, I want to show you guys a little bit of what we just looked at. We had saw that it changed the first derivative changed at around -0.6 and around +0.6. It was square root of 3/3. This is the actual graph. We can see it is going up until we get to around -0.6. Then it's going downwards till around 0.6 and back up. And if you look at it, you can see like from -infinity to 0, it does look like it's curved downwards. And right at around 0, the curvature starts changing and goes back up. So we can see that concavity there. So I thought maybe looking at the actual graph would be beneficial. Let me switch back over to doing some more. So let's sketch. Let's just not have f of x. But we're gonna say y equals f of x. Let's say f of 3 equals 2. And let's say f prime of 3 equals 0. And we're gonna say the concavity is greater than 0 on negative infinity to 3. And it's. Let's change that. Let's make it. No, I have it the way I want it. We're gonna make it less than 0 on 3 to infinity. And let's sketch what the graph might look like.
Both those are working with two double primes.
Yeah,
Would so shouldn't f of 3 equals 2b prime and f of. Did you miswrite it or no?
did I miswrite what?
No.
This is f prime of 3. This is definitely first derivative.
Oh, okay, okay.
So y equals f of x doesn't tell us shit. We just know we have a function. F of 3 equals 2 tells us we have a point where x equals 3 and y equals 2. There is a point there. And f prime of 3 tells us that the slope is 0. So we have a couple options here. I'm gonna sketch all 3. So this part is saying concave up. And this part is saying concave down. So one option I could have without knowing what the derivative, first derivative is anywhere else. Is I could be concave up like this. And then concave down like this. I could be concave up like this. Concave down like that. There's actually a fourth option. Make room for all 4. I could have concave up like this. Concave down like that. And finally, I gotta have the one where it curves up on the left. And it's going down on the right. Only one of these graphs is any good. Which graph is correct and why? And why aren't the others correct? Yeah.
The bottom right one is correct.
The bottom right one is the valid one. Why is this one not correct?
Because the slope is 0, so it can have a positive slope at.
Yeah, this does not have f prime of 3 does not equal 0 there. In fact. What it has, it's not an asymptote, but it's got. It's got an undefined slope at f prime of 3 there. It's got a vertical tangent line at right there. What's wrong with these two? What's wrong with this one? So why did you choose this one?
Because the other two don't look like functions.
Well, that's not very nice. We can have step functions, we can have all sorts of functions, they don't look like traditional ones, a piecewise function can do this. So this has a slope of 0 here. What about f prime of 3 here and here?
Oh, because there's no limit or.
These are both cusps. So the f prime 3 is not gonna equal there, it's also gonna be undefined there.
Is it because they're very rapidly just going?
It's a rapid instantaneous, it's not rapid, but instantaneous change. Picture absolute value of x is the easiest example to see. It's an instantaneous change of slope, and it never goes like transitions by going over 0. So that doesn't have a slope of 0 there either. And again, this is an inflection point. So I've mentioned inflection points a couple times. Let me give you a little more information on them, so you have like something to go with it. If f is continuous, this is required. At x naught, the point we're looking at. And the concavity of f changes direction there. Changes sign there. Guess it's changing direction too. Then. X naught and f of x naught is an inflection point. Give you a nice little math definition to go with it.
And what is X not referring to?
This is my x naught right there. The point, the x value, x naught is the x value where the inflection point occurs. Here I have 3, but I can't just say at 3 because that's not true on every graph. So we use x naught as a dummy variable race basically to say what x value does, where does this occur at? Alright, let's take a look at start at 4.2, we will not finish today. But this is on relative extrema. And this is starting to be actually where we lead into. Maybe even graphing some polynomials, maybe not today, but we'll see how it turns out. So extreme is a weird word. Extrema is plural for extrema. Which is also a weird word. Right? But extremum means. Extreme stuff. Is going on, so one of them would be a minimum. And the other option where we have extreme things happening is at a maximum.
Right, we're not referring to limits, right?
No. Does everyone know what the word minimum and maximum mean? I cannot assume that, because if you don't know, this is a fucking meaning of this discussion. And I need to go over it, but if you know what a minimum is. It's the lowest value. I can always just write it. And the largest value, or highest value.
Not just referring to on a graph.
Yes. We'll do it on a graph in a second, but I'm just saying the words in general, what they mean. The plural form of this. Is minima. And the plural form of this is maxima. Which is why you'll see the words maxima and minima and extrema. Throughout this and what they mean, like knowing what they mean is kind of helpful. Extrema and extremum is the weirdest ones. I think if you saw maxima and minima. You might be able to get the idea of what it's about, at least a minimum and a maximum. Maybe not the plural part, but it's there. So. I can have a graph that does something like this. What would the minimum look like on this graph?
That bottom curve is, plant block curve.
The minimum is negative infinity, the graph keeps going down forever, it's negative infinity. I'm
Okay.
getting to where you're going. What would be the maximum here? Positive infinity, over here. That's just like. Over the whole function. So when we say the word relative. Relative, we are looking at relative is small areas. Is in a small area. Or small region. And this is where I would say we would have. Things happening here, here, and here. This is a minimum or a relative minimum. Maybe I'll write it down below, right here. Relative minimum. Or minima. Is right there. And right there. Relative maxima. Is right there and right there. And that's why we use the word relative, because a lot of graphs. on one side or the other, or both, go to infinity or negative infinity. So, but like, these values matters, shit's changing there. And in the world, a lot of this decision making happens there. If you're in economics, you often have a parabola going downward and you want that maximum, because that's the maximum profit. You wanna maximize your profit, and so finding where that maximum matters in economics. There's uses for all of this here. But that's the general what's going on here, so let's get into some words for it. Other than just the definitions or like descriptions for words. Everyone clear on what like a maxima and minima is? Okay. So we say that a function has a relative max. At x naught. If there is an open interval. A to B. Containing x naught. So x naught's in the region. On which. F of x naught. Is the largest value. What does that mean? It means f of x naught is greater than f of x for all x in the interval. Same thing with relative min. But f of x naught is the lowest value. Or smallest. So f of x naught is less than f of x. And I'm gonna use a symbol where we have a capital A upside down. This symbol here is shorthand for all. And they typically add in equal portion. Because since we're not talking about the overall maximum and overall minimum. If there's another point that's exactly the same. Like if you look at the graph of sine and cosine. The relative minimum is 1 or -1 and the relative maximum is +1. On both curves. Sine and cosine both have a max and min of -1 and 1. And you can go out further and other values, other points are gonna have that same max. But they're still all relative maxes and relative mins. There's some dude, his name was Fermat. Fermat had a theorem. And it feels like a little bit of a no shit theorem. But it's like this. If f of x has a relative extrema. So either max or min at C. And f prime of C exists. then f prime of c has to equal 0. So you're looking at like, you've got curves like that, curves like that. We can look at an absolute value here.
Oh, just talking about the slope.
He's talking about the slope. So we have relative extrema here. Those are all relative extrema, maxes or mins. These ones don't have a slope of 0, it's undefined because of the cusp. But here it's positive, 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 negative, negative, negative. F prime of c equals 0 there. Here the slope is negative there, positive here. It transitions there, F prime of c equals 0 there. Once you look at the picture of it, you're like, yeah, that makes total sense. They go through a proof of it, and it's worth showing you, just so you get used to seeing how math proofs work. We'll prove the maximum one, and the minimum is very much the same. Or maximum. I'm gonna go back up here to f of x naught is greater than or equal to f of x. So we're looking at f of x naught is greater than or equal to f of x. And that's my c, maybe I should say f of c. Which means if I look at values around it. F of c should be greater than or equal to f of c plus some small value h. So like x plus a little bit or x minus a little bit. Looking up here, if this is f of c, this is like an f of c plus h right here. And over here, I could have f of c plus a different h. But the idea is like pictorially what's going on here. Which means if I subtract f of c from both sides. Or alternatively, I'm gonna write it the other way. I'm gonna write it with f of c plus h minus f of c on the left. And the 0 is towards the alligator mouth. So this is where we start, that's our starting thing. So if h is greater than 0, like we're to the right. Then I can divide both sides by h. And it doesn't change the inequality. This also holds. Does that make sense? I'm dividing by a positive number. I should still be less than 0.
Yeah, it looks a lot like the definition of derivative.
That's where we're going. Then we're gonna slap limit on here. And with that limit, we have, that means f prime of c is less than or equal to 0. So that was h was greater than 0. What if h is negative? H is less than 0. Like to the right. Or to the left, sorry. What happens to the sign of f of c plus? This was less than or equal to 0, if I divide by a negative value. What happens to this inequality symbol?
Flips.
It flips. And we'll do the limit here as well. And we get f prime of c is greater than or equal to 0. So putting them together. I have 0 is less than or equal to f prime of c, which is less than 0. What does that tell me f prime of c equals?
Can only be 0 because.
It can only be 0. It's gotta be strictly, it's gotta be greater than or equal to 0, and it has to be less than or equal to 0. The only way this happens is we're squeezing in on it. This is the squeeze theorem. The only way that happens is f prime of c equals 0, and that's what we were trying to show. F prime of c equals 0. Where at this point, the inequality symbols aren't really doing anything. If we switch this around, is it still true? So the converse of this theorem. Is changing the order. And we want to know, is this true? If f prime of c equals 0. Then f of x has an extremum at c. Any ideas?
So would C in this case be the slope,
No, c is the value at x where this slope is 0. It's an x value, we have a slope of 0 at that point. Do I have to have a relative max or a relative min there? No, why not?
In the last example, we had a slope of 0, but it wasn't an x.
The last example was perfect, we had a slope of 0 and. It wasn't a max or min. So no, the converse is not true. So we say. That we have a definition for another thing, critical point. Critical point. Spell critical point right. Helps if I start in the right spot. A critical point. Let's say x naught. Or a function f of x. is any value x in the domain, it's gotta be in the domain. Where a f prime of x not equals 0. Or b f prime of x naught does not exist. This latter one happens when the denominator is 0. And to distinguish between these two things, we call this one is called a stationary point. And as we saw from the last thing. Just because it equals 0, a stationary point. May or may not. Have. A relative extrema there. As we can see right here, this one does.
And this doesn't apply to us, right?
Right, so let's look at some pictures real quick. Some graphs real quick and see where and which ones it apply to. So here's some graphs of some critical points. And what's going on. Let me sketch it, we're gonna sketch a bunch. We'll start off this one. This is x naught. And we'll draw a few. So maybe I'll label these A, B, C, D. E, F, G, and H. Which of these have a relative max or a relative min? E and F have a relative max and min. Anything else?
A and B.
A and B. Yeah, we were comparing this, the last thing we talked about was. How does this track with the derivative? So let's look at the derivative around each of these points. What's the derivative to the left on A? What's the derivative to the left? Is it positive or negative? What?
Which one?
On A, to the left, what's the slope?
Oh.
Slope is positive, so the derivative is positive over here. And on the right, it's negative. Right? So here I'm looking at f prime of x below. What about on B? It goes from negative to positive, right? What about on C? Both positive. D? Both negative. And all four of these top ones, A through D. F prime of C equals 0. The slope exists, but it equals 0 there. If we look down here, this has something similar for each of the slopes. This is positive on the left, negative on the right. This is negative on the left, positive on the right. This one is increasing on both of them. And this side is decreasing on both of these. But on E through H, f prime of x does not exist. On G and H, we end up. We have f prime equals something over 0. So we have like a vertical tangent line. So my tangent line is that. Here, it just doesn't, on E and F, it just doesn't exist. The slope instantaneously changes. There's nothing going on there. I can't even write it like this because there's nothing, I don't have any way of doing it. And that'll be it for today. We'll do something called the first derivative test and second derivative test. You guys want to go over the group, do the group exam thing on Tuesday or Thursday? One of the days we're finishing this lecture and doing 4.3, the other day we're doing group exam. Who wants to do the group exam on Tuesday? Raise your hand. Who wants to do it on Thursday? All right, we'll do the next part of this lecture on Tuesday, the group exam on Thursday. And the week after that, we'll do our exam.